Section: Introduction. In this section, we explore how scaling up model parameters and dataset size has improved next token prediction accuracy in large language models, leading to significant advancements in artificial intelligence. We acknowledge that training on all available data may not always be the best approach. Therefore, we recognize the importance of data filtering through various heuristics and classifiers to enhance data quality and model performance. Despite these efforts, high-quality datasets still contain noisy tokens that can disrupt training. Removing such tokens may alter the text's meaning, while being overly strict in filtering could exclude valuable data and introduce biases. Moreover, we understand that the distribution of web data may not align with the ideal distribution for downstream applications. Common corpus at the token level may include challenging tokens that are hard to predict accurately. Applying the same loss to all tokens can waste computation on non-beneficial tokens, limiting the potential of large language models. To delve deeper into how language models learn at the token level, we analyze training dynamics, focusing on how token-level loss evolves during pre-training. Our findings reveal that there are easy tokens that are already learned, and hard tokens that exhibit variable losses and resist convergence, leading to ineffective gradient updates. Based on these insights, we introduce RHO-1 models trained with a novel Selective Language Modeling (SLM) objective. This approach involves training a reference language model on high-quality corpora to score tokens based on the desired distribution, filtering out unwanted tokens. We then train a language model only on tokens with high excess loss between the reference and training model, focusing on tokens that benefit downstream applications the most. Our experiments demonstrate that SLM significantly improves token efficiency during pre-training and enhances performance on downstream tasks. It effectively identifies tokens relevant to the target distribution, leading to improved perplexity scores on benchmarks. The effectiveness of SLM is evident in math continual pre-training, where RHO-1 models outperform baselines and achieve state-of-the-art performance using fewer tokens. In general pre-training, SLM enhances performance across various benchmarks, particularly in code and math tasks. By selecting tokens strategically during training, we can stabilize the model's trajectory and improve its efficiency. Section Summary. In this section, we explore how language models learn at the token level by analyzing the training dynamics of token losses during pre-training. We observe that only a small percentage of tokens experience significant loss reduction, while the majority have already been learned or remain persistently challenging. By introducing Selective Language Modeling (SLM), we can selectively train language models on tokens that exhibit high excess loss, leading to improved efficiency during pre-training and enhanced performance on downstream tasks. Section: Overview. In this section, we introduce a new approach called Selective Language Modeling (SLM), inspired by the concept of reference modeling in document-level filtering. Our method involves three main steps, as shown in the figure. We first train a reference model on a carefully curated high-quality dataset. This reference model then evaluates the loss of each token in the pre-training corpus. Finally, we selectively train the language model, focusing on tokens with significant excess loss between the training model and the reference model. The idea behind SLM is to prioritize tokens with high excess loss as they are more conducive to learning and align better with the desired distribution. This naturally filters out tokens that are irrelevant or of low quality. Now, let's delve into the details of each step. Firstly, we start by creating a high-quality dataset that represents the desired data distribution. We train a reference model, ERM, using standard cross-entropy loss on this dataset. The ERM is then used to calculate the token loss within a larger pre-training corpus. By computing the reference loss for each token, we establish a benchmark for selective pre-training, enabling us to concentrate on the most influential tokens in language modeling. In causal language modeling, CLM, the cross-entropy loss function is employed. On the other hand, SLM focuses on tokens with high excess loss compared to the reference model. The excess loss for a token is defined as the difference between the current training model loss and the reference loss. We introduce a token selection ratio that determines the percentage of tokens to include based on their excess loss. This selective training approach ensures that the model learns primarily from tokens that contribute the most, enhancing efficiency without extra pre-training costs. In our experiments, we pre-trained models in both mathematical and general domains to evaluate the effectiveness of SLM. For the mathematical reference model, we collected a dataset of high-quality math-related tokens. In contrast, the general reference model was trained on a corpus from various open-source datasets. We conducted experiments to analyze the impact of SLM in continually pre-trained models to assess their performance. For math pre-training, we used datasets like OpenWebMath, while in the general domain, we combined datasets like Slim Pajama and StarCoder data with OpenWebMath. We set specific learning rates and batch sizes for pre-training in each domain, along with token selection ratios tailored to the model size. By integrating SLM into our pre-training process, we aim to improve the efficiency and effectiveness of language modeling tasks. Section Summary. In this section, we propose Selective Language Modeling, SLM, inspired by reference models for token-level data selection in language modeling. Our method involves training a reference model on high-quality data, evaluating token loss, and selectively training the language model on tokens with high excess loss compared to the reference model. By focusing on tokens with high excess loss, we aim to improve the alignment with the desired distribution and exclude irrelevant or low-quality tokens efficiently during pre-training. Section: Baseline Setting. In this section, we utilized models like Tiny Llama CT and Mistral CT, which have been continuously pre-trained through causal language modeling, as our baselines. We also compared our model, RHO-1, with popular baselines such as Gemma, Qwen 1.5, PHI 1.5, DeepSeek LLM, DeepSeek Math, CodeLlama, Mistral, Minerva, Tiny Llama, LLemma, and Intern LM2 Math. Additionally, we compared our fine-tuning results with previous top-performing models Mammoth and Tora. To evaluate the pre-trained models thoroughly, we tested their ability to perform well with minimal training examples and how they improved with fine-tuning across various tasks. We used different setups for general tasks and math-related tasks, and we employed VLLM v0.3.2 to speed up the evaluation process. More details on our evaluation can be found in the evaluation section of our paper. When testing our models with few-shot chain of thought (COT) examples, we found that RHO-1 Math showed significant improvements in accuracy compared to models that were directly pre-trained. For instance, RHO-1 Math achieved an average accuracy improvement of 16.5% on 1B models and 10.4% on 7B models. After further training on OpenWebMath, RHO-1's accuracy increased to 40.9%. Notably, RHO-1 7B, pre-trained on 15 billion tokens, showed comparable results to DEEPSEEKMATH7B, which was pre-trained on 500 billion math-related tokens, highlighting the efficiency of our approach. In our tool-integrated reasoning tests on the Tora corpus, RHO-1-1B and RHO-1 7B achieved state-of-the-art accuracies on math tasks. RHO-1 also demonstrated generalizability on unseen tasks, with notable accuracy improvements on various datasets. We confirmed the effectiveness of our approach by continually training TINYLLAMA 1.1B on 80 billion tokens, resulting in an average enhancement of 6.8% across different benchmarks compared to direct continual pre-training. The improvements were particularly significant in code and math tasks, surpassing 10%. By selecting tokens for pre-training based on a reference model, we observed that the model trained on selected tokens showed a more significant decrease in downstream loss, leading to improved performance. This selection process proved to be more efficient compared to pre-training on all tokens. Additionally, we found a positive correlation between the loss of selected tokens and downstream task performance, emphasizing the importance of token selection for optimal model performance. Section Summary. In this section, we utilize continually pre-trained models like Tiny Llama CT and Mistral CT as baselines and compare them with various top-performing models. We evaluate the few-shot capabilities and fine-tuning performance of these models across different tasks, showcasing significant improvements in accuracy with our RHO-1 model, especially in math-related tasks. Additionally, our approach of selecting tokens for pre-training demonstrates enhanced downstream task performance, indicating the efficiency of this method over traditional pre-training approaches. Section. What tokens are selected with SLM? In this section, we aim to analyze the tokens selected by the SLM method during pre-training to better understand how it works. We visualize the token selection process while training RHO-1 using Open Web Math. In our analysis, we found that the majority of tokens chosen by the SLM method are related to mathematics, which helps train the model effectively on mathematical content from the original corpus. We also looked into how token filtering varies across different checkpoints during training and tested the perplexity of these tokens at each checkpoint. Our observations showed that tokens selected by later checkpoints tend to have higher perplexity in the later stages of training and lower perplexity in the earlier stages. This suggests that the model first focuses on optimizing tokens with a larger learnable space to enhance learning efficiency. Additionally, we noticed a pattern where the perplexity of selected tokens initially increases and then decreases, which could be due to selecting tokens based on higher loss to improve learning at each checkpoint. We further investigated the impact of token selection ratios of the SLM method. Typically, the selecting ratio is determined by heuristic rules, similar to those used in training masked language models, MLMs. Our analysis indicated that selecting tokens accounting for around 60% of the original tokens is suitable. Apart from our main experiments using the same base model for reference and continual pre-training, we explored whether a smaller reference model could effectively guide the pre-training of a larger model. Using TINYLLMA 1.1b as a reference model and continual pre-training Llama 2 to 7b on math, we found that leveraging the small reference model for token selection can benefit the pre-training of the larger model, despite the size difference between them. We also discussed the importance of optimizing pre-training data to enhance language model training performance and efficiency. This optimization process involves improving the quality and scale of the pre-training data mixture through various methods such as data collection, deduplication, filtering, and selection. Furthermore, we delved into the dynamics of language model training, focusing on understanding their behavior throughout the training process. Our research identified different token patterns, including easy tokens and hard tokens, that show varying levels of convergence during training. We proposed a selective language modeling approach targeting influential tokens to optimize the learning process. Lastly, we discussed scaling laws in language models, which help us understand the impact of factors like parameter count, data size, and compute on model performance and behavior. Our focus was on studying token loss of desired distributions, unlike most scaling laws that analyze cross-entropy loss on all training tokens. Section Summary. In this section, we analyze the tokens selected by the SLM method during pre-training to understand its functioning better. By visualizing the token selection process during training, we observe that the majority of tokens chosen are mathematically related, enhancing the model's training on relevant corpus parts. Additionally, investigating token filtering across checkpoints reveals a pattern where tokens selected later have higher perplexity initially, suggesting an optimization strategy for learning efficiency. Section. Scalability. In this section, we have only tested our method on smaller models with up to 7 billion parameters and smaller datasets containing less than 100 billion tokens due to budget limitations. Smaller models benefit greatly from focusing on important tokens and excluding irrelevant ones. However, larger models trained on extensive data may naturally learn to compress useful information, even though it may seem inefficient at present. Future research should investigate if our selective language modeling technique can be applied to very large models and datasets. To evaluate tokens, a high-quality reference model is essential. This reference model can be a base model trained on a small set of high-quality data or a high-performing open-source model. We can even use more powerful proprietary model APIs to obtain input log probabilities or perplexity as reference scores. Various extensions of selective language modeling can be explored, such as reweighting tokens instead of selecting them to enhance robustness, using a reference model as a reward model for guiding pre-training with reinforcement learning, employing multiple reference models to prevent overfitting, implementing token-level curriculum learning, and iterative strategies for continuous enhancements. Selective language modeling can also be extended to supervised fine-tuning to tackle noise and distribution mismatches in many datasets. Additionally, it can be applied to alignment tasks by training a reference model to prioritize helpfulness, truthfulness, and harmlessness, resulting in a base model that is naturally aligned during pre-training.